today I am starting the third unit, that is performance of long transmission lines. Okay, basically the transmission lines are divided into three types, that is short transmission line, medium transmission line and long transmission line. Okay, depending upon the length of the transmission system, the transmission lines are divided into three types. Okay, that is the short transmission line, medium transmission line and long transmission line. Okay, in the second unit we study about the performance of a short and the medium transmission line. Okay, for every transmission system or line having the three parameters, that is resistance, inductance and capacitance. Okay, due to that parameters we are having the sum of the losses. Due to that losses we reduce the efficiency and also we affect the voltage regulation. Okay, that's why we study about the short, medium and long transmission lines. Okay, in the previous classes we already discussing about the short and the medium transmission line, what is meant by the short transmission line and what is the equivalent circuit diagram and what is the phasor diagram for that short transmission line, and how we will calculate the voltage regulation and efficiency for that short transmission line, and also we calculate the generalized constants for that short transmission line, that means the ABCD parameters of the short transmission lines. Okay, and also the medium transmission line is divided into three parts on the basis of the connection of capacitance. Okay, in the case of a short transmission line, only the affected parameters are the R and the L. We neglect the capacitance value because the length of the short transmission line is very less. Okay, for that reason the effect of capacitance is negligible. For that reason only we consider the resistance and the inductive reactance in the case of a short transmission line. Okay, but in the case of a medium transmission line, we are considering the capacitance also. The length of the transmission line is increases, automatically the effect of capacitance is also increased. Okay, in the case of a short and a medium transmission line, the parameters are to be taken as a lumped parameters for easy calculation purpose. Okay, for easy calculation purpose we are taking the lumped parameters in the case of a short and medium transmission line. Okay, in the medium transmission line, depending upon the capacitance connections, that will be divided into three parts, that is end condenser method, nominal T method and also nominal pi method. Okay, in each and every method are having the equivalent circuit diagram and separate phasor diagrams. By using that equivalent circuit diagram and phasor diagrams, we determine the efficiency and voltage regulations easily. Okay, we determine the efficiency and voltage regulations and also sending and receiving end voltages, that all will be calculated by using that equivalent circuit diagrams and also phasor diagrams. Okay, but in the case of a medium and short transmission line, we are considering the parameters are taken as a lumped one. Okay, for easy calculations, the parameters are taken as the lumped form. But in the case of a long transmission line, while we are considering the lumped parameters, the result are not obtained accurately because the length of the transmission line is very more when compared to the short and medium transmission line. If the length of the transmission line is increases, in that case we are using the lumped parameters, the result is not accurately obtained. Okay, for that purpose, in that case, we are using a uniformly distributed parameters. Okay, for that reason, the calculations of this long transmission line is somewhat difficult when compared to the short and a medium transmission line. Okay. First, what is meant by the long transmission line? Okay, the length is above the more than the 200 kilometers. The length is more than 200 kilometers. Then it is called as the long transmission line. Okay, the length of the transmission line is more than the 200 kilometers. It is called as the long transmission line. Okay, in the case of a long transmission line, the resistance, inductance and capacitance and conductance are added. The resistance, the effect of resistance, inductance and capacitance and conductance are included in the case of a long transmission line. Why the capacitance value will be added in the case of long transmission line means the length of the line is increases. If the length of the transmission line is increases, automatically the effect of this capacitance is also increases. Okay, the line constants, that is resistance, inductance and capacitance and conductance of a transmission line are uniformly distributed over the entire length of the line. Okay, in the case of a long transmission line, while you are drawing the equivalent circuit diagram, in the case of a long transmission line, while we are drawing the equivalent circuit diagram for that long transmission line, in that case the resistance, inductance, capacitance and conductance of that lines are uniformly distributed over the entire length of the line. Why you are taking the uniform distribution of these parameters means that the length of the transmission line is high when compared to the medium and short transmission line. If the length of the transmission system is high, in that case the effect of resistance, inductance, capacitance and also conductance are morely added. Okay, due to that effect of resistance, inductance and capacitance, conductance, we are reducing the efficiency of the transmission system. Okay, what is the effect of resistance and what is the effect of inductance and what is the effect of capacitance, that all will be calculated separately in the case of a long transmission line, because the length of the line is very high when compared to the medium and short transmission line. If the length of this transmission line is increases, then automatically the effect of resistance, inductance, capacitance and all the parameters effects are morely added. Okay, that's why we reduce the efficiency and also that will be affected in the voltage regulation also. Okay, in that case we are using the lumped parameters, the result are not obtained accurately. Okay, why? Because the result are not obtained accurately means that if the length of the transmission line is increases, automatically the resistance, inductance and capacitance values also increases. While we are taking the lumped one, that means we are taking only, we are considering the one resistor, one inductance and one capacitance in the case of a medium and short transmission line. Okay, but in that case the length of the line is less, therefore the effect of resistance, inductance and capacitance is also reduces. Then overall we calculate the result for that effect of resistance, inductance and capacitance. There is a small variation for usage of uniformly and lumped parameters, for usage of uniformly and lumped parameters. Okay, that is the main reason for considering the uniform and lumped parameters. Okay, suppose we are assuming the one resistance, one inductance, one capacitance means that is the lumped one, then the calculations is made easy. Okay, that already we observed in the case of a short and a medium transmission lines. Okay, but coming to the long transmission line, if you are taking the lumped constants. The line has a lumped constants and line calculations made with such assumptions gave the result with reasonable accuracy. Okay, reasonable accuracy. If such an assumptions of lumped line constants is applied to the long lines, serious errors are introduced in the line performance calculations. Okay, while taking the lumped constants of resistance, inductance and capacitance and conductance in the case of a lumped forms in the long transmission line, by using that lumped form of these parameters, we obtain the serious errors are obtained for this line performance. Okay, therefore we are using the lumped parameters is replaced by the uniformly distributed parameters. Okay, for calculation of these uniformly distributed parameters, for normal calculations it is difficult to calculate that type of effect of resistance, inductance and capacitance values while considering the uniformly. Okay, that's why in the case of a long transmission line we are using a rigorous mathematical treatment. Okay, by using this rigorous mathematical treatment we solve the solution for adding the resistance, inductance and conductance are in the form of a uniformly distributed in the case of a long transmission lines. Okay, that is the main reason for considering the uniformly distributed parameters in the case of a long transmission lines. Okay, therefore the performance calculations of long transmission lines are made with line constants uniformly distributed over the entire length of the line. Okay, normally in the case of a short and medium transmission line we are using the lumped parameters. Okay, why we are using the lumped parameters means the for easy calculation purpose, we are taking the lumped parameters. But there is a very small difference between while considering the lumped and the uniform parameters. That's why we neglect that small difference in medium and the short transmission line. But in the case of a long transmission line, while we are using the lumped parameters, we are obtaining the serious errors. Okay, while using the parameters are having the lumped parameters, we are obtaining the serious errors. Okay, that's why in the case of a long transmission line we are using only uniformly distributed parameters. Okay, the resistance, inductance and capacitance values are to be considered as a uniformly distributed. Okay, that is the main reason for the lumped and the uniform distribution of parameters in the case of long transmission line. Okay, this is the equivalent circuit diagram. Equivalent circuit diagram or single line diagram for a long transmission line. Okay, in that case this is the R by N and X by N. Okay, this is the transmission line sending end side and this is the receiving end side. Okay, this is the transmission line, this is the sending end side and this is the receiving end side. In the sending end side we are connecting the generating station. Okay, in the receiving end side we are connecting the load. Okay, the length of this line is very high, very high, that is greater than 200 kilometers. Okay, the length of this long transmission line is greater than the 200 kilometers. Okay, the length of this line is greater than the 200 kilometers. Okay, that's why we are taking the lumped parameters is replaced by uniformly distributed parameters. Okay, these are all the uniformly distributed parameters, that is R by N, X by N. Okay, this is R by N, X by N, and swan R by N, X by N. Okay, up to nth term, we are having the resistance and the reactance. Up to nth term, we are having the resistance and the reactance, and this is also conductance and the susceptance is also added. Okay, next this is the Vs is the sending end voltage and Vr is the receiving end voltage. Okay, this is the total equivalent circuit diagram for a long transmission line. Okay, this is the sending end side and this is the receiving end side. Sending end side we are connecting the generating station and receiving end side we are connecting the load end. In between the sending end and receiving end we are having the uniformly distributed parameters for resistance, inductive reactance, and capacitance and conductance. Capacitance and the conductance. Okay, these parameters are to be uniformly distributed. Okay, this is up to and swan n parameters we are having. Okay, that's why we have taken as R by N and X by N, B by N and G by N. Okay, the whole line is divided into n sections. Okay, the whole transmission line, the whole long length transmission line is divided into n sections. Is divided into n sections. Okay, each section having the line constants, each section having the line constants 1 by nth of this for the whole line. Each section having the line constants, that is 1 by nth of this whole line. Okay, this is the overall equivalent circuit diagram of a long transmission line. In the case of a long transmission line, this is the sending end side and this is the receiving end side. Sending end side we are connecting the generating station, receiving end side we are connecting the load. Okay, in between sending end side, receiving end side we are having the uniformly distributed parameters. Okay, this is the resistance and this is the reactance. Okay, these uniform parameters are having the line constants of 1 by nth of these constants, 1 by nth of the resistance, 1 by nth of the reactance, 1 by nth of the capacitance and 1 by nth of the conductance. Okay, the whole line is divided into n sections, each section having the line constants of 1 by nth of those for the whole line, 1 by nth of those for the whole line. Okay, in that the line constants, that is resistance, inductive reactance, capacitive susceptance and conductance. Okay, the resistance that means R, the resistance that means R, and reactance, inductive reactance that means X, next capacitive susceptance that means B, next conductance that is G. Okay, the next conductance Z. Okay, the line constants, that is resistance, inductive reactance, capacitive susceptance and the conductance. Capacitive susceptance and the conductance are uniformly distributed over the entire length of the line. Okay, are uniformly distributed over the entire length of the line, as is actually the case. Okay, in the case of a long transmission line, the resistance, inductive reactance and capacitive susceptance and conductance are uniformly distributed over the entire length of the line. Okay, the resistance R and inductive reactance XL are the series elements. Okay, in the equivalent circuit diagram, the resistance R and the inductive reactance X are the series elements. Okay, the capacitive susceptance, that is B, and leakage conductance, that is G. Okay, the capacitive susceptance B and leakage conductance, that is G, are the shunt elements. Okay, are the shunt elements. Okay, in the case of equivalent circuit diagram, the resistance R and the inductive reactance X are the series elements. Okay, the resistance R and the inductive reactance are the series elements. Okay, the capacitive susceptance B and the conductance G are the shunt elements. Okay, this is the overall equivalent circuit diagram. In that equivalent circuit diagram, the resistance R and the inductive reactance X are the series elements, and the capacitance, the capacitive susceptance and the conductance are the shunt elements. Okay, these elements are uniformly distributed over the entire length of the transmission line. Uniformly distributed over the entire length of the transmission line. Okay, thus the shunt admittance means it will be represented by Y. Okay, the shunt admittance that is represented by Y. Y is equal to the square root of G square plus B square. Okay, Y is equal to the square root of G square plus B square. Y is the susceptance, shunt admittance. Y is the shunt admittance is equal to the square root of conductance square plus capacitive susceptance square. G is the conductance and B is the capacitive susceptance. Okay, therefore Y is equal to the square root of G square plus B square, where G is the conductance and B is the capacitive susceptance. B is the capacitive susceptance. Okay, in the case of a long transmission line, the parameters are to be taken as a uniformly distributed parameters. Okay, what are the parameters? That is resistance, inductive reactance, and capacitive susceptance and conductance are to be taken in the form of a uniformly distributed load. That already we observed in the equivalent circuit diagram. This is the uniformly distributed parameters. R and resistance and the inductive reactance are connected in series, and capacitive susceptance and conductance are connected in parallel. Okay, this lumped uniformly distributed parameters are calculated by using this rigorous method. Okay, it does not calculated for the normal procedure for distribution of that uniformly distributed elements. That's why we are using the separate method. Okay, నార్మల్ మెథడ్ తో మనం క్యాలిక్యులేషన్స్ అనేది చేయలేమమ్మ. ఫర్ ఇన్ ద కేస్ ఆఫ్ ఏ యూనిఫామ్లీ డిస్ట్రిబ్యూషన్ లో నార్మల్ మెథడ్ లో మనం క్యాలిక్యులేషన్స్ అనేది చేయాలి అంటే ఈచ్ సెక్షన్ కి R/N సెక్షన్స్ ఉంటాయి. R/N సెక్షన్స్ కి మనం సపరేట్ గా క్యాలిక్యులేషన్స్ అనేవి చేసుకుంటూ చాలా లాంగ్ ప్రొసీజర్ ఫాలో అవుతూ దాన్ని బట్టి మనం ఓవరాల్ గా ఆ పారామీటర్స్ వల్ల ఎంత ఎఫిషియన్సీ ఉంది అనేది, ఎంత లాసెస్ ఉన్నాయి అవన్నీ కూడా మనం క్యాలిక్యులేట్ చేయగలం. కానీ అది చాలా రాంగ్ ప్రాసెస్. అలా ఈచ్ అండ్ ఎవ్రీ పారామీటర్ కి మనం క్యాలిక్యులేట్ చేయాలంటే చాలా డిఫికల్ట్ ప్రాసెస్. కాబట్టి మనం ఏం చేస్తామంటే ఒక స్మాల్ లెంత్ డిఎక్స్ అనేది తీసుకొని ఆ స్మాల్ లెంత్ లో మనం తీసుకున్న పారామీటర్స్ వల్ల ఎంత ఎఫెక్ట్ ఉంది ఆ ఎఫెక్ట్ ని మనం క్యాలిక్యులేట్ చేసుకొని దాన్ని ఓవరాల్ గా మొత్తం పారామీటర్స్ ఉన్నప్పుడు ఎలా ఉంటది అనేది ఇంటిగ్రేషన్ చేసుకొని దాన్ని బట్టి సొల్యూషన్స్ అనేవి ఈజీగా మనం చేసుకోవచ్చు. కాబట్టి ఈ మెథడ్ ని మనం ఇలా చేస్తే మొత్తం ప్రాసెస్ ని మనం ఏమంటున్నాము అంటే rigorous method of solution of a long transmission lines. Okay, in the case of a short and medium transmission line, we are taking as a lumped parameters. That's why we calculated directly. Okay, but in this case we are using the uniformly distributed parameters. But in this case we are using the uniformly distributed parameters. Okay, by using these uniform distributed parameters we are not supposed to calculate the for regular process. for that reason we are using the rigorous method of solution. Okay, by using this rigorous method we calculate the performance of this long transmission line. Okay, the rigorous method means that we consider a small length dx. We consider the small length dx. By considering the small length dx, we are calculating the effect of that parameters, and then overall we integrate that effect of parameters, and then we calculate the overall efficiency and regulation, and also ABCD constants for that transmission line easily. Okay, the total overall calculations are to be considered as the rigorous method. Why we are using the rigorous method means that rigorous method, that means that in the case of a long transmission line, the elements are to be taken in the uniformly distributed parameters. For uniform distribution parameters we calculate the performance of each and every element separately is very difficult process. Okay, that's why we are using the rigorous method. First of all, what is meant by the rigorous method? Rigorous method means that long transmission line. In that long transmission line, this is the long transmission line. In that long transmission line, we are considering a small length dx. In that small length, what is the effect of that resistance, and what is the effect of that inductive reactance, and what is the effect of capacitive susceptance, and what is the effect of the conductance, that all calculated in this particular small length. After that we integrate that small length value, then we obtaining the overall length of the long transmission line. Okay, by integrating this small length value, that we obtaining the overall length of the transmission system. Okay, that's why this is the simple process for calculation of long transmission line. Okay, otherwise we are calculating the uniformly distributed parameters is difficult. Normally we are calculating the uniformly distributed parameters, that is very difficult in the case of a long transmission line. In that long transmission line means the length of this line is very high. We are having the n number of parameters, n number of resistance, and n number of inductive reactance, and n number of capacitive susceptance, and n number of conductance are there. Okay, that's why we are not calculating each and every parameter effect not easily. For that reason we are using the separate method, that is the rigorous method. Okay, by using this rigorous method we are easily calculating the how much percentage of efficiency will be reduced for the effect of these parameters, that all will be calculated easily. Okay, rigorous method means in that long transmission line we are taking a small length dx. Small length dx we are having the effect of the resistance, inductive reactance, and also capacitive susceptance and conductance are there, and then we calculate that effect, and then we integrate effect, and we obtaining the overall effect of this long transmission line easily. Okay, that is the analysis of a long transmission line or rigorous method of solution of long transmission line. Okay, that is the main reason why we are taking the rigorous method in the case of a long transmission lines. Okay, this is the long transmission line diagram. In that we are taking the small length dx. Okay, this is the small length dx. In that small length dx we are having the z parameter, and this is the small length dx. In that also we are having the y parameter. Okay, this is the overall small length dx. Okay, small length dx. First taking a x meters distance from the receiving end side. Okay, consider x meter distance from the receiving end side. Receiving end side nunchi oka x meter distance lo manakunna overall length lo receiving end side nunchi x meters distance lo మనం ఒక స్మాల్ లెంత్ x అనేది తీసుకున్నాం. ఓకే, ఆ x మీటర్స్ డిస్టెన్స్ లో ఒక స్మాల్ లెంత్ dx అనేది కన్స్ట్రక్ట్ చేసుకున్నాం. దట్ స్మాల్ లెంత్ dx విల్ బి represented in the dotted lines. Okay, the small length dx that will be represented in the dotted lines. Okay, this is the dx. How you are taking that dx means that at the receiving end side of this transmission line we are taking the x meters distance from the receiving end side. In that x meters distance from the receiving end side, then we considering a small length dx. Okay, receiving end side nunchi x meters distance తో ఒక small length dx అనేది assume చేసుకున్నాం. receiving end side నుంచి ఒక x meters distance తో ఒక small length dx అనేది మనం assume చేసుకున్నాం. Okay, this is the dotted line indicates the small length dx. In that small length dx, the parameters are the z and the y. Okay, what is the z? Z is equal to square root of r square plus jxl. R is the resistance, xl is the inductive reactance. Small length means that we multiplied with z dx. Okay, z into dx, and then this is the y, that is the y into dx. We considering the small length, that's why we multiplied by dx. Y is equal to the square root of g square plus b square. Okay, g is the conductance and b is the capacitive susceptance. B is the capacitive susceptance. Okay, next this is is the sending end voltage and vs is the sending end current. Okay, the is is the sending end voltage and vs is the sending end current. Okay, after that this vr is the receiving end voltage and ir is the receiving end current. vr is the receiving end voltage and ir is the receiving end current. Okay, and x is the small length that will be taken at the receiving end side. X meters distance we are taking at the receiving end side, and then dx is the small length that will be taken at the x meters distance from the receiving end side. Dx is a small length that will be taken at the receiving from the receiving end side of the x meters distance. Receiving end side nunchi x meters distance తో ఒక small length dx అనేది మనం కన్స్ట్రక్ట్ చేసుకున్నాం. ఓకే, in that we represent the this dx, this length is that will be represented in the dotted form. That will be represented in the dotted form where z is the impedance and y is the susceptance. Y is the susceptance. Okay, next one is the I plus di, where I is the current. I plus di is the current entering at the small length dx. Okay, I plus di is the current entering at the small length dx. Next one is the I is the current leaving from the small length dx. I is the current leaving from the small length dx. Next, v plus dv. V plus dv is the voltage across the small length dx. Okay, v plus at the sending end side. V plus dv is the voltage across the small length dx at the sending end side. Okay, v plus dv is the voltage across the small length dx at the sending end side. Okay, I plus di is the current entering at the small length dx and v plus dv is the voltage across the small length dx. V plus dv is the voltage across the small length dx. Okay, next I is the current leaving from the small length dx. I is the current leaving from the small length dx. Next one is the v. Okay, v is the voltage across the small length dx at the receiving end side. Voltage leaving at the small length dx at the receiving end side. Okay, the total transmission line having the length of a L meters. Okay, the length of this transmission line as the L meters. Okay, in that L meters at the receiving end side, from the receiving end side to x meters distance, we are taking the small length dx. Okay, dx is the small length at the receive. Total overall length is the L meters. In that L meters at the receiving end side, from x meters distance, we are taking a small length dx value. Okay, this is the neutral, and V plus dV is the voltage across this small length dx at the sending end, and I plus di is the current entering at the small length dx. Okay, I plus di is the current entering at the small length d. Okay, the total length of this transmission line is the L. At the receiving end side, we are taking the x meters distance. From the x meter distance, we are taking the small length dx. Okay, in that small length dx, we are having the z dx and the y dx. We are taking the z dx and the y dx. Z is equal to the square root of r square plus xl square, and y is equal to square root of b square plus g square. Okay, I plus di is the current entering from this small length dx, and V plus dV is the voltage across this small length dx at the sending end side, and V is the voltage across this small length dx at the receiving end side. Okay, I is the current leaving from this small length dx, and VR is the receiving end voltage, IR is the receiving end current, and VS is the sending end voltage, and IS is the sending end current. Okay, this is the circuit diagram or equivalent circuit diagram for the calculations of rigorous method. First of all, what is meant by rigorous method? Rigorous method means the uniform distributed parameters are to be calculated by considering a small length dx in the case of a long transmission line. Okay, that means the length of this transmission line is L. That the total length of this transmission line, we are taking only a small length dx value. Okay, in that length we calculate the effect of this z and effect of this y. After that, we integrating these effects, and then we obtaining the total parameters effect for the total length of the L. Okay, how we will taking this dx? From the receiving end side, we are taking the x meters distance. At that x meters distance, we are considering the one small length dx. Okay, this method is called as the rigorous method. Okay, consider a infinity small length dx of the line at a distance x meters from the receiving end. Okay, let R is the resistance per unit length of the line, and x is the reactance per unit length of the line. Okay, therefore z is equal to square root of this r square plus x square. Next, b is the susceptance per unit length of the line, and g is the conductance per unit length of the line. Therefore, y is equal to the square root of b square plus g square. Okay, therefore z is equal to square root of r square plus x square. Okay, that is the impedance per unit length of the line. Okay, that is the impedance per unit length of the line. Okay, next one is y. Y is equal to the square root of g square plus b square. Square root of g square plus b square. Okay, that is called as the admittance per unit length of the line. Okay, where V is the voltage per phase at the end of the elements towards the receiving end. V is the voltage per phase at the end of the element towards the receiving end. Okay, V plus dV is the voltage per phase at the end of the element towards the sending end. V plus dV is the voltage per phase at the end of this elements towards the sending end. Okay, VR is the voltage per phase at the receiving end and Vs is the voltage per phase at the sending end. IR is the current per phase at the receiving end. Is is the current per phase at the sending end. Okay, therefore I plus di is the current entering the element dx. Okay, dx is a small length, considering a small length dx. Okay, in that the entering current is the I plus di. Okay, and I is the current leaving the element dx, and I is the current leaving the element dx. Now the series impedance of the element dx of the line. Okay, the series impedance of the element dx of the line is the z dx, is the z dx. Okay, the shunt admittance of the element, the shunt admittance of the element dx of the line is the y dx. The shunt admittance of the element dx of the line is the y dx. Okay, the rise in voltage over the element length in the direction of the increasing the x. Okay, increasing the x. Next, dv is the iz dx. Okay, dv is equal to the iz dx. Voltage drop in the element dx. Okay, the voltage drop in the element dx, that is dv. The voltage drop in the element dx, that is dv. dv is equal to the iz into dx. Okay, that is the various parameters that will be considered in the case of a rigorous method of solution of a long transmission line. Okay, this is the rigorous method solution of a long transmission line. By using this solution, we determine the overall performance or overall losses that will be obtained for these two parameters, that is z and y. Okay, after that we integrating these losses, then we obtaining the overall loss obtained due to that overall parameters, that all will be calculated easily by using this rigorous method of solution of a long transmission line. Okay, this is the analysis of a long transmission line, basic introduction. Okay, by knowing these terms only, then we calculating the derivation for that small length dx, the affected parameters for the small length dx, while we knowing these terms. Okay, the R means the resistance, X is the reactance, B is the susceptance, G is the conductance. Therefore, Z is equal to the square root of R square plus X square, that is the impedance per unit length of the line. Y is the G square plus B square, that is the admittance per unit length of the line. Then V is equal to the voltage per phase at the end of the element towards the receiving end. V plus dV is the voltage per phase at the end of the element. Okay, we already well known about the VR, VS, IR and IS. Only the new terms is the I plus DI. Okay, the I plus DI is the current entering the element, that is DX. Okay, DX loki enter అయ్యే current ఏంటి మనకి I plus DI, and then I is taken as the current leaving the element dx, or current leaving the element dx, and series impedance is the z dx, shunt admittance is the y dx. Okay, therefore the voltage drop in the small length dx is dv. dv is equal to the iz into dx. dv is equal to the iz into dx. Okay, this is the various parameters that will be considered in the case of a rigorous method of solution of a transmission line. Okay, next class లో దీని derivation చేద్దాం అమ్మా.